An ideal gas undergoes four thermodynamics processes shown in figure below, during which process the gas does positive work. The four thermodynamic processes refer to A to B, B to C, C to D, D to A, where the A, B, C, D are the states, four different states of the gas in the process. Now we imagine that the gas is in a cylinder with a piston on top. When the molecule of the gas bombard the piston and the piston move up, so the gas expands. The force from the gas is points upwards. This is a force. And the displacements of the piston also points upwards. So from here we can note that the work done by the gas in this case when the piston move up, or we say that when the volumes of the gas increase, the work done by the gas, the work done from the force exerted by the gas is positive. So that means when the gas is expand, the work done by the gas is positive. But now if we consider the piston is moving down due to an external force pressing on the piston and force the piston to move down, the force from the gas that bombard on the piston also points up. So that means this force will against the movements of the piston. The displacements of the piston is pointing down. So that means the force, the vector force, and the directions of the vector displacement x, they are opposite directions. Now, if it is opposite directions, the work done by the force from the gas is negative work done. So that means when the gas is compressed, the work done by the gas would take the negative sign. The work done is negative. Now we write down the result of our analysis about the relationship between the change of the volumes and the sign of the work done by the gas. For the first case, when the volume change is positive, that means gas expand, the work done by the gas is a positive value. When the gas compress or the volume change is negative, volumes become smaller, then the work done by the gas would take the negative sign. So that means that to know the sign of the work done for the four thermodynamic process shown in this diagram, we need to know how the volumes of the gas change, whether the gas expand, compress, or remain the same. If it is remain the same, that means work done by the gas is equal to 0. But the problem is in the graph, we cannot read or get the informations about the change of the volume directly from the graph of the P versus T. P is the pressure of the gas in Pascal, and the T is the temperature of the gas in Kelvin. So we cannot read directly, get the information directly from this graph of P versus T. This is the things that we need to think about. How to know about the change of the volume from this graph, so that we can know, we can deduce the sign of the work done in these four thermodynamic processes. To deduce the informations about the volumes change of the gas from this P versus T graph, we can apply the ideal gas law which is a PV equal to nRT, and if we change the P as a subject to get P equal to nR over V times T, and we apply this to the graph of P versus T. So in the P versus T graph, if we compare with the equation of straight line, which is y equal to mx plus c, that means the y is the P pressure in this graph is the y, and the T in this graph is the x. So that means nR over V is equal to the gradients of the graph, and the C, which is the intercept of the line of the graph, would be equal to 0. So that means if we connect a line, we get a line that connecting the origin and the states and the 4 states shown in this diagram, then we would able to know what is the gradients of the line. And from the gradient, we will know about the informations about this volume. If the gradient is larger, that means the volume will be smaller. If the gradient is smaller, that means the volumes of the gas V would be bigger. Okay. Now we consider these two lines. One is connecting A and D and pass through the origin. Another one is the passing through the B, connecting B and C, and then pass through the origin. So that means these two lines, the equations would take this form, and the gradients would be, in this case, would be related to the would be equal to nR over V. So from these two lines, then we know that state A and D, they have the same volume, and state B and C, they have the same volume. And since the gradients of this line is larger than the gradients of this line, that means the volumes of the A and D, which is equal volume in A and D, must be smaller than the volume of the B and C. Volume B and C also the same. So these two volumes, the volume of these two states, would be the same as the volumes, would be the larger than the volumes of these two states, because this line's gradient is less than the gradients of this line. With the informations about the volumes of the 4 states A, B, C, D, now we can easily to analyze about the work done of the gas when it changes from one state to another state. We start from A to B. So from A to B, since the volumes of the A is smaller than the volumes of the B, therefore delta V would be larger than 0. That means this is expansion. So the work done when the state changes from A to B, the work done by the gas would be positive value. From B to C, the volumes doesn't change because state B and state C, they have the same volumes, so delta V equal to 0. Therefore, the work done by the gas when the state change from B to C is equal to 0. The work done equal to 0 because there is no change in volume. From C to D, the volumes is become smaller. Therefore, delta V is less than 0. Delta V will take a negative sign. And the work done by the gas when the state change from C to D also will take the negative sign, because this is a compression. When the gas compress, work done negative. When the gas expand, work done positive. In the last process, where the state change from D to A, there is no change of the volumes, no compressions, no contractions, no expansions. Therefore, the V remain the same. So the work done by the gas when the state change from D to A will be equal to 0. So that means for the 4 processes that form the cyclic process, only the process when the state change from A to D, A to B, the work done by the gas is a positive value. To summarize, these questions require us to deduce the information about the volumes of the gas from the graph P versus T. This graph P versus T does not allow us to get the information of the V directly from the graph. It is not the P versus V graph, which is commonly seen in the thermodynamics. This is a V versus T. So that means the challenging part is that how to get the information of the V from the P versus T graph. Once we know the information about the volumes of the gas and we know how the gas volume change, then it would be easier for us to know for these 4 processes which one the gas will do the positive work, which one will do the negative work, and which one the work done is equal to 0.